Going live. One.
So you're not going live. Okay. Good morning. Good morning. You're welcome to this live stream. It's a pleasure, I should say, to have you all here. We just started, so
Nobody's here. Relax.
we are waiting for. Wait.
Friends face.
We are waiting for as many people as possible who would join. We are waiting for as many people as possible who join. Please, as an engineering student, please get your friends to join. Okay, all your friends, tell them of how expedient and paramount it will be to join this class. You are going to learn a lot, I should say. You're going to learn a whole lot. The introduction to all the algebra you will do. We are going to see the introduction. So, and the introduction is very, very important and very key, because if you start right, then you start well. So this introductory class to Algebra Math 151 will be your stepping stone to greatness. Now, if you want to get 100% in this course, you can get 100%. If you want to get 95, you can get a 95. If you want to get, Papa, say now we are live. A bunch time. You want to get a 50%, you can get a 50%. So more people are joining. Let's keep our fingers crossed and allow many people to join. We'll start soon. Okay. We said 10:30. So we'll be starting soon. But before we start, if you have any questions, type it in the chat box. If you have any question, type it in the chat box as we wait for the others to join. Any question at all? Okay, I see you, Kingsley Asante. Good morning to you too. Outrex too. Welcome. Please get your friends to join from other departments as well. It mustn't be from electrical engineering. Doris Nyame, good morning. Good morning. Any item it's in Jamal. I'm preparing some meals in my room, so after the class you can come to my place for some food. Please. Kingsley Okran, the mid-semester exams will come on, but as of now, because lectures haven't begun, we don't know when the mid-semester is, but there is going to be a mid-semester exams for everyone in due time. Okay, thank you very much. I hope I've answered your question. Please call your friends. We have to. Okay, how long will the class last? The class will last at most an hour. We will not exceed 1 hour. Okay, will not. So please, before you type your question too, you can say, okay, electrical engineering, computer engineering, aerospace, so that we know your department before you type your question. Okay, the class will last for an hour at most an hour. But trust me, it will be worth it. So just stay tuned. Hey, Joshua wants to know my room. Wow. Okay. Oh, Joshua, don't worry. I'll put my room number out there after the class, okay, so that you can come for your item 13. Please don't forget to type your department and then you ask your question. So okay. So I mean, all of us. Okay, I'm Kingsley Okran is from computer engineering. So Kingsley Okran, please get some of your friends to come on board. Okay, your friends in the class. Send it to your class group. Yeah, send it to your class group. Yes, Doris, I mean, mid-semester exams is for everyone. First year, second year, third year, fourth year. You are going to write mid-semester exams. But for now, we don't know when it is as it stands now. Yes, please. So all engineering students will be reading applied electricity, and we will all be doing technical drawing, and we'll all be doing algebra. So this ELEESA live tutorial session will be on applied electricity and algebra, and then probably there will be some specific courses. But for now and for today, we'll be doing applied and algebra. So the applied will be at 3:30 in the afternoon. So what about the other courses like engineering technology and technical drawing? Yes. So engineering technology and technical. So let me tell you about engineering technology. Engineering technology is department specific. What I mean by that is that every department will be doing different things when they go to the engineering, when they go to the lab. So the engineering technology is more of lab work. So you will go through all the labs that your department will be using in the 4 years. So for electrical engineering like this, we went through the wiring lab, we went through the instrumentation lab, we went through computer lab. So the engineering technology is department specific. You go through your labs. Okay. Technical drawing too is for everyone, but we will not be doing technical drawing for these live streams. We won't be doing technical drawing for these live streams. So the book I'll be using is this Math 151 Algebra 2016. It's a PDF that is available to many of you. I know that because it's a PDF that your lecturers will be using. So it's Math 151 Algebra 2016. Math 151 Algebra 2016 PDF. So if you have it, open it. If you have it, get it set. If you have it, get it set. So right now we are about 49. I'm thinking when we get to I'm thinking when we get to 70 we can start. Or if any of you disagrees and wants us to start, I mean you can share your views. If you want us to wait for your friends to, you can let us know. Okay. Please, there is a quiz. Now you don't find this tutorial session anywhere in KNUST and even in the world. You don't find it anywhere. So you are lucky to be a part of it. There is a quiz after this session. Okay, so we have sat down the academic board together with all stakeholders and our tech guy, Pakwansa. Yes. So we sat down and we set some questions on what we'll do today. So after the live stream, you just click the link to the questions is in the description box below. So right now it's locked. You can't answer the questions, but after the live stream, we'll open the portal so that you can answer the questions. Okay. All right. So I'm seeing. Let's start. Okay. So we'll start at 10:45. We'll start at 10:45. 10:45. Like you're alive. Please, any more questions? Any more questions? So my name. Okay. What do I know about the strike? Okay. The strike, I have very little information on it, but what I know is that when they went to court yesterday, they were asked to settle the issue, which is the NLC, the National Labour Commission, and the UTAG were asked to settle the issue out of court. Okay, so and return back on 10th February. So we are supposed to hang on board and wait for the outcome of their discussions. So let's get started. My name is Kelvin Tamakloe Worlanyo Kwabna. My name is Kelvin Tamakloe Worlanyo Kwabna. I'm the Vice President for Electrical and Electronics Engineering Department. Electrical and Electronics Engineering Student Association. I'm the Vice President. Okay. The name of the PDF is Math 151 Algebra 2016. Math 151 Algebra 2016. Yeah, so that's the type. That would be there. Okay, so a drive containing the Math 151 PDF will be sent soon, okay? So that you can all access it if you don't have it. So we are starting. So a link has been sent right now as I'm speaking to you. So open the link and go to Algebra, go to books. No, not books, but open the link, go to Algebra and find the Math 152 PDF in it. So open Sem 1. Okay, so it will be Sem 1. Then you open Math 151 Algebra. Okay. Then you open slides. You open slides, so it's there. Okay, it's there. So let's start. So you're looking at the introduction. The introduction to complex numbers. The introduction to complex numbers. All right. So we all know this basic equation that was used to find the solution to quadratic equations, right? So we all know something that was called the almighty formula. We saw that to find the roots of a quadratic equation, we can use x is equal to minus b plus or minus square root of b squared minus 4ac over 2a. So this formula gives us the roots of the quadratic equation. And we saw that this term here, b squared minus 4ac, is called the discriminant. Okay, I'm arriving somewhere, so just follow me closely. This term is called the discriminant. Okay, And we said that this term b squared minus 4ac gives us the nature of the solutions or the roots to the quadratic equation. So we saw that if b squared minus 4ac is equal to 0, okay, we saw that, then it means that the quadratic equation has repeated roots. It has a single repeated root. So a graph of it will look like this. It will look like this, touching the x-axis at a single point, just a single point. You follow? I'm arriving somewhere, okay? So the graph of it will touch the x-axis at a single point. The x-axis is referred to as the real number line. So it has repeated real roots. Now, in the case where this b squared minus 4ac is greater than 0, then we saw that the quadratic equation has two real but distinct roots. So here to touch the x-axis or the real axis, the real number axis at 2 points. Okay, you follow? Now, there was another situation where we saw that b squared minus 4ac is less than 0. And we said that in this situation, the quadratic equation has no real roots. It has no real roots, meaning that a graph of it will not touch the x-axis, which I called the real number axis. So a graph of it is not touching, so it has no real root. Then what does it have? It has complex roots. It has complex roots. So before now, we live in a world where we were told that, oh, if I have an equation like x squared plus 1 is equal to 0, I want to find x, I'll say, okay, x squared is equal to negative 1. X will be equal to plus or minus square root of negative 1. And then we'll end here. Now we are being introduced to another world where we don't end here. This square root of negative 1 has a notation. And this is the introduction of complex numbers. Knowing that when the discriminant is less than 0, we say the quadratic equation has complex roots. It doesn't touch the real number axis. Okay. What does this mean? This is the same as finding the square root of a negative number, because we can see that if we can see here that if b squared minus 4ac is less than 0, it means there's a negative number here. And before we were told that square root of negative numbers don't exist, but now they do exist and they are not real, they are complex. So this is what brought about the introduction of complex numbers. Let me go to a new page. The introduction. So we saw that square root of negative 1 now exists, and it is represented by the letter I. It is represented by the letter I. You follow me? So let me go back to the math. Let me go to the math 151 slide and read. Okay. So all this side, I've spoken about all this side, the fact that we have square root of a negative number represented by, and square root of negative 1 represented by the letter I. Okay, right? Or J. When you are doing in engineering, when you are doing applied electricity and pure engineering, basic mechanics, you see that anywhere you're supposed to use a complex number, they use J, because we know that current is I. So using I and I for current and I for complex numbers in applied electricity will be confusing. So I or J. So look, I, and in engineering, they would use a small j to represent complex numbers. Okay. So The general form of any complex number at all is, let me write it as this: a complex number z, okay, can be represented as x plus y I. Any complex number that exists in this world can be represented as x plus yi. Let's see what x and y are. Okay, so this x here is a real component or the real part of the complex number, and the y is the imaginary part of the complex number. The imaginary, I for imaginary, the imaginary part of the complex number. So notations, of course, mathematics use notation. So I can write that re subscript z, re subscript z, meaning the real part of the complex number z is equal to x, and I can also write im subscript z as, which represent the imaginary part of the complex number z, is equal to y. Okay, so these are just notations. If you see them anywhere, just know what they mean. If you see rez equal to something, know that you are talking about the real part of a certain complex number, and imz is the imaginary part of a certain complex number. Hello? Okay, so I can have a complex number, say z being equal to 2 plus 3i. I can have a certain, let me say this z1. I can have z2 to be equal to 1 minus i. These are all complex numbers. So you can see that I have my real component in z1 to be 2 and my complex part to be 3. Okay. I can have another complex number to be, let's say, 4i. This complex number has no real part. The real part is 0. So it's like having my 0 plus y, but of course 0. I mean, no one writes 0. So z3 can be 4i. It's also a complex number. Okay. All right. So this is the introduction to complex numbers. Once you understand this, you are good to go deeper into the complex numbers we are about to study. Okay. Now, writing complex numbers this way it means that you are representing the complex number in the rectangular form. So writing a complex number to have a real part x plus an imaginary part yi means the complex number is written in the rectangular form. As we go on, we'll see that complex numbers can be represented in other forms, in another form. Okay. For those who have read, it's called the polar form. But for now, we are looking at only the rectangular form of complex numbers. Okay. Let me go to the next place. Right. So, like numbers, like all numbers, like real numbers we have been dealing with all our lives, we can do algebra to complex numbers. We can add complex numbers, we can subtract complex numbers, we can divide complex numbers, we can multiply complex numbers. And it's not difficult at all. It's not difficult at all. If you did algebraic expression in class 6, yes, Akiola, People's Book 6, page 45, it is there. Addition of algebraic expressions. You can go and check if it's at page 45. All right, that was just by the way. Okay. Yes, I've been talking for a long time, so I had to put something funny there. Okay, so addition of complex numbers, we add complex numbers like how we would do any addition at all. Okay. If I have a complex number, let's say z1, let me come here. If I have a complex number z1, z1 is equal to, let me say, 3 plus 4i. I have my z2 to be equal to 2 minus 2i. And I say, okay, z3 is equal to z1 plus z2. Hence, evaluate or find z3. And I'll say that, okay, my z3 is equal to z1 plus z2. My z1 is 3 plus 4i plus my z2 is 2 minus 2i. Now, you add them component by component. What I mean by that is that you add real to real and complex to complex. So if you're adding complex numbers, you add the real part of the first complex number to the real part of the second complex number, and then you add the imaginary parts of the complex number to the imaginary parts of the other complex number. So here, I'll just take, okay, I'll have my 3 plus 2, okay, which gives me 5, and I'll have 4i plus negative 2i. So 4i minus 2i giving me my 2i. So addition of complex numbers is not difficult at all. It's not difficult at all. It's like the algebraic expressions, with I being a variable. So you add like terms, let's say that here. So 3 plus 2, 5, 4i minus 2i, 2i. And that is all for addition. So no matter what you are supposed to add, no matter the number of complex numbers you are supposed to add, just add real to real and imaginary to imaginary. Same for subtraction. So I can ask you to find Z4, which is equal to Z1 minus Z2. So my Z4 will be equal to Z1. Z1, which is 3 plus 4i, then minus Z2. If you are doing subtraction, it is always expedient to be bringing the brackets. If you don't bring the brackets, you'll be confused. So minus 2, let me count down here, right? So 3 plus 4i in brackets minus into bracket 2 minus 2i. So same, expand, let me say 3 plus 4i minus 2 plus 2i. So real for real, 3 minus 2, 1. Imaginary for imaginary, 4 plus 2 plus 6i. And that is the addition and subtraction of complex numbers. So we can see here the notations are here using variables, but it's the same thing. Okay. So there's an example here. We see sum the complex numbers I 1 plus 2i, 3 minus 4i minus 2 plus I. So real for real, 1 plus 3 minus 2, 2. Imaginary for imaginary, 2i minus 4i plus I, negative I. So all in all, we'll get a final answer to be 2 minus I. There are about 5 other examples there that you can try. So you should try them out after the class. Okay. Now let's see. So equality of complex numbers is not anything, it's not any big deal at all. If a complex number, let me say, if a complex number z1 is equal to x plus yi, and a complex number z2 is equal to a plus bi, and I tell you that z1 is equal to z2, then it stands to reason that x is equal to a. The real part of complex number 1 is equal to the real part of complex number 2, and the imaginary part of complex number 2, and the imaginary part of complex number 1, sorry, is equal to the imaginary part of complex number 2. So equality of complex numbers is not a big deal. It just means that if two complex numbers are equal, then their real components are the same, and their imaginary components are also the same. Okay. So there are quite a number of examples here, and addition and subtraction of complex numbers that we can try out. Now, let us move on to something very, very important. That is the modulus and argument. The modulus and arguments of complex numbers. Finding the modulus and argument of a complex number. Now, before that, when we did vectors, we saw that vectors in senior high school, we know that, okay, vectors can be represented in a Cartesian plane. If I have a vector like, let me say 3i plus 4j, This vector can be represented as 3 on the x-axis, right? So 3, then 4, then I can draw like this. My vector is moving here with my arrow. This is same for complex numbers. So a complex number can be represented in a Cartesian plane, which has a special name. When it comes to complex numbers, the Cartesian plane has a special name called the Argan Diagram. ARGAND. This is the Argan Diagram. Okay. The x-axis represents the real axis, and the y-axis represents the imaginary axis. Okay. So if I have a complex number z as 4 plus 2i, this means that this complex number has 4 on the real axis and 2 on the imaginary axis. So it will pass through this point. So this is how this complex number will look like. Fantastical. That's it look like. You follow? So once I know the real and the imaginary components of a complex number, I can represent it on the Argan diagram. If I have another complex number like, let me see, 3i, this complex number has no real part, only an imaginary part. So it will be 3 here. It will lie here. 3 on the imaginary axis. Does it make sense? It should make sense. It should make sense. Okay. So Aram, you have a question. You said that if we have complex numbers adding or subtracting, okay, and then the imaginary component goes to 0, does that make the number a complex or a real number? It's a complex number with an imaginary component of 0. To some extent, real numbers are complex numbers without an imaginary component. You get me? So it is a complex number without an imaginary component, making it a real number. But once you're adding two complex numbers, you are getting a complex number as your answer. Yes. So for example, let's say you have a complex number like z. Complex number z is equal to 2. Can be asked to draw this on the Argan diagram. So that will be this, the real component. I have my 2. So it is like this. So in forces, I could have said that it's a force without a y component. Yes, if you did your mechanics very well, and I mean you are engineering students, so I'm sure you are all the young and brightest in one class. So okay, let's move on. So this is the Argan diagram. Okay, it has a real component and an imaginary component. Any complex number can be represented on the Argan diagram. Okay, sure. So now we can go to finding the modulus is the magnitude of the complex number. Okay. So the modulus represents the magnitude of the complex number. Let me write it for you to see. Finding the modulus and the arguments of complex numbers. Modulus and arguments of complex numbers. So if I have a complex number z represented as x plus y I, then modulus of z, right, can be represented as, or is equivalent to writing mod z. It's the same as writing bar of z. So all these are notations for representing modulus. Okay. Quite often than not, people use the last one, the bar. So I'll say that modulus of z, which is the magnitude of z, is equal to square root x squared plus y squared. This is a formula, you must know it. It's not a difficult formula. You've seen it as finding the magnitude of a vector. So you just take square root of the sum of the square of the real component and the imaginary component. That'll give you the modulus of z. Okay, so Doris didn't get the Argan diagram for 3i. So let me go back. So 3i is 3i is a let me show you here. Let me show you here. 3i is a complex number without a real part. So which means that if I have a number line like this and I'm seeing that this is the real part and this is the imaginary part, okay, and z is a complex number 3i and has no, so this 3i is the same as me saying z is equal to 0 plus 3i, right? So the real component is 0, so I'm here, 0, 0, I'm here, okay, and my imaginary component is 3, so I'm here. So this complex number will lie on the imaginary axis. I hope it makes sense now. So a complex number without a real component has a real component of 0. So it's like you're plotting points. So I'm at 0, 0, 0, 3, then plot the points. I hope it has made so same for if it was a real number like such as 3. It means this complex number has no imaginary component. We have an imaginary component of 0, so plus 0i, and then a real component of 3. That will give me this and that. So I hope it makes more sense now. If not, you can still ask for further clarification. Okay, so we were finding modulus and arguments of complex numbers, right? Like I said, this is the formula to find the modulus or the magnitude of a complex number. So for a complex number z is equal to 5 plus 12i. Find mod z. So you can try it. So mod z will be equal to the square root of the x component squared plus the y component squared. So please try and post your answer. Post your answer down. I'm solving anyway. So the square root of 5 squared plus 12 squared. And that will be giving me 13. On your calculator to give it 13 units. 13 units. So finding modulus is not any difficult thing at all. It's the easiest question you can ever get in your algebra test, and you will not get it like this. You might be asked to do something, and find the modulus of the complex number you get at the end. That's very possible. Let's see this if I was doing before. All right, so that is the modulus. Now, the next concept we'll be looking at is the argument. The argument is just basically the angle spanned by the complex number measured from the positive x-axis. So positive real axis. Sorry. So let me draw my Argan diagram here for you. And we said this is the real axis, right? So real axis, imaginary axis. So if I have a complex number here, the angle created by the complex number measured from the real axis is what we call the argument, represented by theta. Is the argument, in short, arg. So arg z, if you see anywhere you see something like arg z means the argument of a complex number z. It can be anything. Usually they use z for complex numbers, but it can be anything. At all. So this is the arg z, argument of the complex number. So if the complex number was in this region too, then this would be its argument. Okay, this would be its argument. if the complex number was in other regions, we would know where its argument is. Now, the argument, okay, a range of values has been set for the argument. So we will think that, okay, since we are dealing with angles, then the argument should be from 0, 90, 180, 270, 360 degrees. So we will think that the argument should be from 0 to 360 degrees, but this is not so. Okay. Math 151 Algebra 2016 KNUST. A range has been set for the argument, and this range is from minus pi to pi radians. From minus, so this is the argument. Let me put here. Argument of z. So the argument of z ranges from minus pi less than argument of z less than pi. Less than or equal to pi. Less than or equal to pi. This is the range of values. So this is in radians. So it's the same as me writing minus 180 less than theta argument less than or equal to 180 degrees. So the argument can be represented in degrees or in radians. Many a time, we'll be using the argument in radians. Keep it in your mind. The argument will be used in radians. Okay. So that's what we have. Now let's talk about the argument into more details. Depending on where the complex number lies, the arguments will be gotten differently. Let me explain that. So we know that, okay, if I have a Cartesian plane like this, I have my first quadrant. Let me show you. I'll have my first quadrant here. First, I have my second quadrant here. I have my third quadrant here. And my fourth, sorry. I have my third quadrant here and my fourth quadrant there. So a complex number can be in the first quadrant, in the second quadrant, in the third quadrant, or in the fourth quadrant. So these are all complex numbers. These are all complex numbers. Imaginary, real, imaginary, real. Right. So there's a formula for the argument, but let me explain something to you. Let me come here. So we can see that the argument of z is equal to tan inverse of y over x. This is not entirely true, right? This is not entirely true. The argument of z is equal to tan inverse of y over x is not entirely true. Based on the quadrant the complex number lies, we will adjust this equation. Okay. So preferably, I don't call that equation argument of z. Okay. That equation is just an alpha, a certain alpha angle. The acute angle with respect to the imaginary, to the real axis. So let's say here's alpha. Here's my alpha. Okay. Here's my alpha. Here's my alpha. So alpha, I would say, is equal to tan inverse of y over x. What is this y over x? If I have a complex number z to be equal to x plus yi, this complex number has an x component, or what, a real component of x, an imaginary component of y. Okay, so I can get a right angle triangle from this with an angle alpha. So then if I have x real, and I have y imaginary. Then my alpha, let me say tan alpha, opposite over adjacent. Therefore, my alpha is equal to tan inverse. My alpha, let me say alpha is equal to tan inverse of y over x. So that's how the alpha came about from the right angle triangle. So here too, my alpha will be equal to tan inverse of y over x, tan inverse of y over x. Now, I said early on that the alpha represents the angle of the complex number measured from the positive real axis. So here, this is my argument. Here, this is my argument in the second quadrant. Okay, when it comes to the third quadrant, we don't measure the argument counterclockwise or anti-clockwise. We measure it clockwise. So we'll see all the adjustments. I'm just saying something. When it comes to the third and fourth, when you have a complex number in the third and fourth quadrant, you measure their arguments from the positive real axis in the clockwise direction. So now let's see how this formula is adjusted to get the argument. So if I have a complex number in the first quadrant, for example, I have a complex number such as 3 plus 4i, and I tell you to find the, okay, let me use I have a complex number 1 plus i, okay, complex number 1 plus i, and I say find the arguments of this complex number. You find your alpha. So you say, okay, your alpha is equal to tan inverse of y over x. Alpha will be equal to tan inverse of 1, which is my y, over 1. Tan inverse of y over 1 is, tan inverse of 1 is 45 degrees. And in radian, so I'm using the radian, pi over 4. So my alpha is pi over 4. If you look in this Argan diagram, you can see that your alpha, which is pi over 4, is the same as the angle from the positive real axis measured in the clockwise direction, which means that then my argument of z will also be equal. So this implies that argument of z is also equal to pi over 4. So in the first quadrant, your argument is equal to your alpha. So in the first quadrant, when you find your alpha as tan inverse of pi over 4, your argument will also be equal to pi over 4. In the second quadrant, so a complex number in the second quadrant can be, let me say z is -1 plus I. The complex number -1 plus I. So if we are to illustrate that -1 in the on the real axis, -1, 1 here. So I'll have this. So I can complete this to form a triangle with my alpha here. So alpha is always the acute angle, acute less than 90 degrees. The acute angle the complex number makes with the real axis, right? Okay. So find your alpha. Same. Alpha is equal to tan inverse of y over x. Now, if you are finding alpha, you are just inputting the numbers. You don't care about the whether y or x is positive or negative. No. So here, my y is 1. So my y is 1. So 1. Although I'll say my real component, I'll say is -1, but no. When I'm finding the alpha, I just put in the values. So like y and x, the positive values. So here to my alpha will be equal to tan inverse of 1 over 1. Tan inverse of 1 giving me pi over 4 radians. But this alpha is not my argument. No. This alpha is not my argument. If you are in the second quadrant, and you want to find the argument, we said the argument is the angle from the positive real axis measured counterclockwise if you are in the first and second quadrant. So let me see. It means I'm here, okay, and now I'm moving here. So, but I found here rather. I found here. You follow? So I found alpha to be pi over 4, but I want to find this angle. Easy. Aquila, page 72. Yes, angles on a straight line sum up to 180 degrees. So 180 radian is pi. So I'll just do my pi. I'll do pi. So my I'll get my argument of z to be equal to pi minus pi over 4, which will give me 3 pi over 4 radians. So generally, for the first quadrant, alpha is equal to argument. Okay, so for the first quadrant, argument is tan inverse of y over x. For the second quadrant, argument is equal to pi minus tan inverse. Let me write it all. Argument is equal to pi minus tan inverse of y over x in radians. Don't forget that the tan inverse of y over x, the y and x, we use the positive numbers. So although z is minus 1 plus I, when I'm finding tan inverse of y over x, I'm using 1 over 1, the positive values of the real and complex. So even some people would want to put absolute values here, absolute value of y, absolute value of x. Same equation. So note this, that in the second quadrant, argument is pi minus tan inverse of y over x in radians. Makes a lot of sense. You're all right. I can see you trying to solve. Very, very right, students. Okay. So in the third quadrant, something different will happen. I told you that in the third and fourth quadrant, we measure the argument clockwise. Okay. So I'll still have to find my alpha. Alpha is always the small angle, the acute angle. So here too, alpha is equal to tan inverse y over x, assuming z is equal to negative 1 minus I. So a complex number, negative 1 minus I, will be in the third quadrant. So my alpha will be tan inverse of absolute value of y over absolute value of x, which is tan inverse of 1 over 1, which is pi over 4. But this pi over 4 is not the argument. So get the difference. It's not the argument. This pi over 4 is the acute angle here. I want to find this angle here. This angle here. Angle here. So I will have to subtract the acute angle from 180. And as if that is not enough, because we are moving clockwise, you would have to negate your answer. So in this analysis, counterclockwise is taken as positive angle. Clockwise is taken as negative angle. So I'll have my argument to be equal to, first I have to get this angle. So angles in a straight line, right? So pi minus pi over 4, that will give me 3 pi over 4, right? But because I moved in the clockwise direction, I'll have to negate this whole thing. So negative. So my answer will be, so I've moved negative 3 pi over 4 radians. In other words, the argument, or in short, the argument in the third quadrant is equal to alpha, which we know is tan inverse y over x in radians minus pi. So when I was in first year, I used to do this. I'll just draw the entire Cartesian plane. Then I'll put, okay, quadrant. So after everything, I'll show you what I used to do. So I'll put quadrant 1. Alpha is argument. Quadrant 2. Argument is pi minus alpha, which is tan inverse over y over x, and so on and so forth. So I'll show you. So this is the general equation in the third quadrant. You see here, I'm taking my time because once you get this side, you are good to go. So don't say, oh, you came, I was slowing down. No. there is more. There is more to come than yes. So let's see. Let's hasten up a little bit. So if I have a complex number in the fourth quadrant, a complex number in the fourth quadrant can be 1 minus I. So 1 on the real minus 1 on the imaginary. So I can form this, have my acute angle here. So my alpha is equal to tan inverse as usual, y over x. Absolute value of y over absolute value of x. So alpha is tan inverse 1 over 1. Tan inverse of 1 is pi over 4, as we've done 3 times already. Here we can see that over here, the alpha is the argument, because if I move alpha degrees, I will hit the complex number. And because I've moved in the counterclockwise, no, I've moved in the clockwise direction, then my argument will be negative pi over 4. Negative because I moved in the clockwise direction. So in short, I can say that in the fourth quadrant, argument of z is equal to negative tan inverse y by x. Negative tan inverse. The acula I'm talking about is the acula you used to using. Please, when are you finding the tan inverse? When you find the tan inverse, that's in the subtraction in front of the number. Okay, so someone is asking that. Okay. Someone is asking that when we are finding the tan inverse, doesn't the subtraction in front of the number matter? No, it doesn't. Okay, the subtraction doesn't matter. So that's why I say that this formula actually is like this. Let me go back. It's tan inverse. Okay, in some books you see it as tan inverse of absolute value of y over absolute value of x. In some books you see this. Okay, so if you are finding the tan inverse, you don't bring the, let me call it polarities. You don't bring whether it's plus or minus. You just use the actual numbers. The polarity, the plus or minus, will give you an idea of how to draw it. So always make sure you sketch. Always make sure you sketch your complex number. Like that is a must. Like you must give a life to Christ to go to heaven. You must. Hey, sorry, I'm Muslim. You must also sketch. Please, you get me? That is sound racist. So you must sketch. So the plus minus makes you know how to draw it, so that you would know which of the equations, whether you are subtracting from 180, you are adding 180, or you will negate or leave it like that. I hope I've answered your question. Okay. I hope I've answered your question. So now let me draw a big Argan diagram. Okay. So argument in the first quadrant, argument of z in the first quadrant is equal to tan inverse y over x. Let me say absolute value of y over absolute value of x in the first quadrant. In the second quadrant, argument is, so this is in radians. Please don't forget, so this is in radians, in rad, okay. In the second quadrant, my argument is pi minus tan inverse y over x, absolute value, absolute value. In the third quadrant, my argument is tan inverse y over absolute value of x minus pi. And in the fourth quadrant, it is equal to negative tan inverse negative y over, sorry, absolute value of y over absolute value of x. So this is the breakthrough. This is the magic brethren that you've all been waiting for. This is all you need from today's class. This is because, like, as you see principal argument, you have to be doing some stuff. You must understand arguments very well. That's why I really took time to explain. So once you know this, that's why I didn't totally agree with, and even your lecturer in class tell you when he's teaching that this arg z tan inverse y by x is not entirely true based on the quadrant. something is done. So don't forget that the argument spans from minus pi to pi. Minus pi less than theta less than or equal to pi. So if you solve an argument and you get 7 pi over 4, you are wrong. Your argument should 7 pi over 4 isn't more than 180 here. Your argument should always be less than pi and greater than negative pi. Less than or equal to pi and greater than negative pi. Okay, sure. So there are a number of examples here. I think there's one mistake in one of them, so just look at it and make sure you know what you are doing. So please, this table is very important. I mean, this final Cartesian plane I've drawn, like me, I used to draw it. It was on my fingertips. So make sure it is on yours too. Okay. When it comes to, so now we are moving on. So far we've seen the introduction, we've done addition, subtraction, equality, we've seen modulus and arguments. Now, when it comes to multiplication of complex numbers, another something that is like something you know in your past. Multiplication of complex numbers is the same as multiplying two algebraic expressions. So expand. So you take the first, used to multiply everything in the second, plus take the second, used to multiply everything in the other. So let's see. Let me use numbers. Let me use numbers. So for example, I have I'm supposed to multiply 1 minus 2i multiplied by another complex number 3 plus 4i. Okay. So 1 for 3 and 4. 3 1 3 4 1 4 plus 4i minus 2i times 3 will give me minus 6i minus 2i. Pay attention here. Pay attention here. Minus 2i minus 2i times 4i. Let's do for the numbers. Minus 2 times 4 is minus 8. Something I should have mentioned early on, like when I started craft, we saw that I was equal to square root of negative 1. I mentioned that, right? I was equal to square root of negative 1. I squared is equal to negative 1. You can see, like, square both sides. Square root cancel square. So I squared is equal. So this is also something. It's not any big deal, but let me mention it. So I squared is equal to negative 1. I squared is negative 1. So let me see. Yeah, good. So here, negative 2 times 4 will give me negative 8. I times I, which is I squared, will give me negative 1. So negative 8 times negative 1. So here, I'm actually getting positive 8 without the I. So there's some basic. Let me just get there. Let me say it right now. So let me go to a fresh page and say I is equal to square root of negative 1. I squared is equal to 1. I cubed is equal to negative I. I4 is equal to 1. I to the power 5 is equal to negative I to the power 121. I to the power 5 is I. I to the power negative 121. Okay, I'm coming. I'll show you this. There's a trick. There's a trick here. There's a trick here. Okay. Okay. So you must know I to the power 2. This is all you must know. I squared is 1. Once you know this, we are good to go. And I to any even power. So I to any multiple of 4. If the exponent, sorry, so I'm getting a little confused here. Okay, just pardon me. But I to an exponent where the exponent is a multiple of 4 will always give you 1. Okay. So you can see that I to the 8, that'll give you I times I, or let me say I to the 4 times I to the 4. I'll give you I to the 8. These are some basic algebra, let me call it this. So once you know I squared is equal to 1 and you know your indices, you should be able to find all the other ones. Like I cube is equal to I squared times I. If I squared is that, then you can find the other one. Okay. So I cube here is I, sorry. Okay, so let's move on. Let's move on. Let me come back here. So here, negative 2i times 4i is positive 8. Then after, when you get here, you just add. So we got addition already. 3 plus 8, 11. 4 minus 6 minus 2i. This will be your final answer. So anytime you are supposed to multiply complex numbers, you just expand and you arrive at addition and you just add them together. Okay, so you can see here, find this. You can see here that you're supposed to find I minus 8i plus 8i, multiplying 1 plus 8i. So 1 will multiply everything here. Negative 8i will multiply everything here. Note when you're multiplying negative 8i times 8i, negative 8 times negative 8 times 8, negative 64. Then times I squared negative 1, so that'll give you positive 64. So we really take note of that. That I squared, you'll be seeing it. I squared is negative 1. You'll be seeing it a lot. I squared is negative 1. You'll be seeing it so many times. So just apply. Okay. Okay. Now there are some properties. Okay. Some properties that you must know that will make life easy for all of us. And multiplication of complex numbers is commutative. You can see here. It's also associative. Okay. Now, if I have two complex numbers, multiplying each other, I have two complex numbers. Let me say z1 times z2. And I say find the modulus of z1, z2. Someone would want to, maybe the complex numbers are 1 minus 3i times 2 plus 3i. And I say, okay, find the modulus of this complex number. Someone would want to multiply, get an answer before he uses the square root of x squared plus y squared to find. But there's a property, there's a property of complex numbers that's very simple. If you are to find the modulus of a product, let's say here, it is the same as me finding the modulus of z1, like this, separately, modulus of z2 separately, and multiplying them. Okay, so yeah, I can find modulus of this one. So I'll do my square root 1 squared plus 3 squared, that's root 10. And also find modulus of z2, square root 2 squared plus 3 squared, that's root 13. Therefore, modulus of z1, z2 will be equal to root 10 times root 13. That'll give me square root of 130. 10 times root 13. Which can become simplify if it's possible. You can write it if possible. It's not compulsory. It's not compulsory. They can specify it, but if it's not specified, radians. If it's not specified, radians, because you want to have that pi beauty is there, like pi over 4, pi over 3. I mean, it's very, very beautiful. Yes. So if it's not specified, radians. If it's not specified, radians. Okay. So the property I want you to note is that the modulus of a product is a product of the modulus of each of the complex numbers. So instead of me multiplying this before I find the modulus of the answer, I can just find the modulus of this, separately, and then I'll multiply my answer. So that is a property. Another property too is if I'm to find the argument. So maybe I have a complex number like this. The complex number 1 minus I multiplying another complex number minus I plus I. And I say find the argument. Find the argument of this. So because you have learned multiplication, you can think that okay, let me multiply this, get my answer, move on from there. But you know that it will be the same as you finding the argument of this one. So argument of 1 plus I. So you draw argument, you draw 1 plus I will be in the fourth, 1 minus I will be in the fourth quadrant. So its argument will be minus tan inverse y over x. Give me minus pi over 4. For the second one too, it will be in the second quadrant. Yes, minus 1 plus I, second quadrant. So its argument will be pi minus tan inverse y over x, pi minus pi over 4, 3 pi over 4. Okay. So once I have the argument of this and the argument of this, then the argument of this complex number will just be argument of z1 plus argument of z2. Very simple. So I'll just have to add this minus pi over 4 plus 3 pi over 4. Okay, that'll give me pi over 2 radians. So the property you are supposed to note is that the modulus of a product is a product of the modulus of each of the complex numbers. And the argument of a product is the sum of the arguments of each of the complex numbers. Nothing difficult here. Everything is clear, simple, and you should be able to wrap your head around everything we have done today. So let me see. Yeah. So we will not start complex conjugate today. Today we are dealing with the introduction. The introduction. So this is where the Lord Almighty has brought us. This is where the Lord Almighty has brought us for today. Please, if you have any other question, keep your questions coming. Keep your questions coming. Okay, so I squared is -1 because someone asked me a question. We saw I was equal to square root of -1. So if you square both sides, you get I squared to be -1. My bad. I made a mistake there. Okay. So I squared is -1. My bad once again. Okay, any other question? Any other question? Please, do you have any other question? How do you get the ebook? The book I'm using. Okay, so I'm sending there's a Google Drive that has electrical course materials, but if you just go inside and look for semester 1, you open Math 151 Algebra, go to slides, you see there. If you go to slides, you see there. So with everything we have done so far, we can answer some questions. Trust me, you can answer some questions. So there are some questions that were set, okay, by the board. Yes, and the members. Some questions have been set in the description box. The questions, they are not open yet. There are 5 questions on what you've done today. As soon as you are done, your marks will come straight forward. Okay, so do it. Even send the questions to your friends. who didn't join the class, because it's to benefit everyone. Share it in your class groups. It's been open now, so you can click on it, answer the questions, so that you know whether you understood what we did today. If you didn't, send us an email. If you didn't, the email is there. So if you didn't, send us an email. Okay. So the questions are very, very, very beautiful questions. Just try your hands on them. They come show the question. So I want to put the questions for you to see. I want to put the questions for you to see before.
And yes, so at 3:30. So please at 3:30, our Excellency Pepra Kwame Ama Frimpong would be taking he'll be taking applied electricity, right? So please tell all your friends. So this is how the algebra practice test looks like, right? So you answer the questions, you get your results right after. Very, very beautiful questions, and then it would take it. So then if you're able to solve them, the first person to quickly solve them would get a prize from our vice president. Yes, so those are the two announcements that we wanted to make. So that is everything. I hope you had a beautiful time. And you can check the description box if you want. You can check the description box if you what you can contact us. Yes, so please, if you've not subscribed, then please subscribe, because in the afternoon we'll be taking apply electricity. Put on your post notifications and everything. Right. Hope you had a beautiful time. Thank you so much. My brother.